Hello and welcome to the second video for alternating currents. So in our first introduction video where we learn what alternating currents are and what is it about and how to describe it using terms like frequency, maximum or peak current or voltage, and also how changing or having a rotating coil in a magnetic flux can create this alternating current. I've also taught you how to look at adapters. So this one is from Huawei. All right. So you see the input here. Okay. And you might be wondering, when we were studying AC just now, I distinctively remember that the AC equation for current looks something like I is equal to I naught sine omega t. Okay, then you might be thinking, if it's this equation, then how and why can we just write 0.5 ampere? Is this the peak current? Is it the actual current? What is the actual current? So currently, right, we are going to move on to the second topic to try to address the issue of what should we label our devices. And because I don't think writing an equation like this at the back of your normal day-to-day electrical appliances will help anyone lah. All right. So this idea or this definition, the need to define alternating current in a way that is relevant to its power output, brings us to the definition of root mean square. Okay, so we are trying to talk about, like, now we know AC keeps changing, but we would much prefer to have an AC value that makes sense to us from our day-to-day rather than a sine curve or a cosine curve. Okay, so with that in mind, we will define the RMS value. So this is what we call an RMS value. And why is it called RMS? Maybe at the end of the video you will see how, but we are going to call this root mean square, RMS. All right. So RMS value of alternating current is the value of the direct current. So we're going to borrow some equations from direct current. Okay. If you don't want to use direct current, you can use direct voltage. All right. That will produce the same heating effect or produce the same amount of thermal energy at the same rate, aka same power output in a common resistor. Okay, so what does this mean? This means that if, let's say for example, I have a alternating current and I pass it through a resistor, the resistor will heat up the same amount as if it is with connected to a DC. Okay, so maybe drawing a circuit will help you understand this. So I'm going to draw a circuit now. Okay, so you can see I've drawn two circuits. There's alternating current, one on the left. This one will be, so normally alternating current, we will define it this way lah. Okay, so we will draw a waveform like this. I'll write the equation of the current. I is equal to I naught sine omega t. So the current flowing inside this circuit will follow this equation and travel back and forth. So there are two directions. Then this one would be a DC current. This DC current that comes out from this circuit that enters this one will be the root mean square current. Okay, so if now what I'm trying to do is I'm trying to find a way to relate I to IRMS. Okay, and the relationship by definition is such that both resistors are going to heat up the same way. So this resistor will get hot and this resistor will get hot and they will have the same power output. All right, so both resistors have the same power output. Look. Okay, so here's a few issues here. You might be thinking, okay, I have a solution, miss. We just need to find the average current. If we can find the average current of the alternating circuit, then that would be a pretty accurate representation of the current of the AC. If that is what you are thinking, you are kind of on the right track, but not really. And here is why. Let me show you the graph again. Okay, so here you can see a good old current graph. Okay, so let me label the axis for you. This will be the current I, and this axis here would be the time t. Okay, don't be too hung up about the constant. I have selected my I naught to be 1 because that will allow you to brain the graph easier. Okay, so this one is I naught. All right, so our first problem is if you look at the average of this graph, so this graph will have an equation of I is equal to I naught sine omega t. Okay, is that you notice that the area is the same, because if let's say I average across these two cycles, right, the average current is 0. Why 0 leh? You see, the area under this orange graph, so this area under this orange graph, and this area under this orange graph, one is positive, one is negative. So if you go and find average of current, it means that the average is 0. So if let's say you want to use the mean of I, mean or average of the AC current, sometimes we will use the bracket. In physics, we will use this bracket for mean. Okay, that arrow bracket. This is 0 because these two kind of cancels out. They kind of like cancels, or the average of these two is 0. Mean I is 0. Hiya. So if let's say the reason why you get 0 is because there are positive and negative values, like for example, if you take this positive I naught, there will be a negative I naught to cancel out. If you take this random point here, there will be another random point here to cancel out. So because of the graph being perfectly symmetrical, every single point on the graph will have an opposing point that is negative value, and you add together, you get 0. So annoying. So what happens when we have a negative sign that we don't want, especially in this kind of statistical treatment, is we will square the graph. Okay, so right now what we're going to do is we're going to square this graph to get the purple one. So this graph here is your I square. All right, rewritten, it will be I naught square sine square omega t. And I can hear everyone panicking. Miss, wait. I'm not good with maths. Okay, if you're good with maths, I'm going to use this identity to derive the equation. But if you're not good in maths, it's okay. I'm just drawing the graph to you so that when you use the equation later, it makes sense. All right. So here, your current, when you square, you get this shape that kind of looks like it, but not really. And you might be wondering why. Well, I chose 1 now. Okay, it can be any other values one. Let me show you. So if my I naught is less than 1, when I square numbers that are less than 1, I will get smaller values. See? Like for example, 0.5 square is 0.25. So whenever we square numbers that are less than 1, you'll get a smaller number. That's why the purple color square graph is below the orange graph. Okay, let's say I increase until more than 1. Like that. You see? If let's say I square 1.5, I get something that is bigger than 1. I mean, bigger than the actual value. So 1.5 square is bigger than 1.5. And you can see that the intersection is just nice at 1. Think about all your graph that you have learned. The intersection here is just nice 1. Okay, where this orange and purple graph intersect. And below the intersection point are values that are less than 1. So the square number is still smaller than the original number. Okay, so I mean, I stuck to 1 because it's easier to see, but this is also okay. All right, so right now, since we cannot find current, so we will just square the current such that the graph is always positive. So you look at this purple graph, always positive. Beautiful. That way your average will never be 0. Okay, and so now the question remains, is this a good enough representation? I think it's okay because the shape doesn't deviate that much, but also at the same time, this graph, this sine square graph that I'm trying to trace out now, when you think about it, right, we are defining this using power. Okay, so when we use power, what is the equation for power dissipated in the resistor? What do you think? Equation for power, this power output, P is equal to I square R. So there are two reasons why we want to square the current. Number one is because there are positive, negative, and squaring it allows us to have a more accurate representation of what is happening here. Because you know why? Our resistor don't care. Our resistor don't care whether your current is flowing from left to right or right to left. As long as there's current, the resistor will get hot. All right? A resistor is a simple circuit component. So since the direction of current doesn't matter, I just need the magnitude, right? So squaring it will be a good enough representation for us at this point. So let's think about what is the average of this, the mean of I square. Okay, so don't forget the peak value is still I naught. So if you want to find the mean of I square, so if let's say this is a purple graph, this is also equal to I naught square. All right, if you don't like this graph, I will paste the second one down there for you. Okay, so this is another graph for you. If let's say you're like, Miss, why are they the same? Okay, they happen to be the same because I chose 1 as my I naught. But if your I naught it's not 1, this will be I naught, and ding, 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 this is I naught square. Okay, so if I want to find the mean square of I square, so this graph is I square, okay, and the orange one is I. What do I do? All right, so there are a few ways to look at this, okay? The actual proof actually needs more mathematics, or you need to do some integration, because what we're trying to do is we're trying to find the average of this current over time, all right? But if let's say you're not really that interested in maths, but you notice that it is a significant handicap when studying physics, right? Okay, so let's say you're not really that interested in maths and you're like, I just want to know what the mean square value is, because this one, when you talk about I square, this is the mean of I square is also known as the mean squared current. Okay, so to find the mean square current, what we'll do is we square everything already, okay, and then you think to yourself, what is the value of this mean square current? Like, what is the average of the purple graph? Okay, so the purple graph, right, has many values. Okay, I'm going to rub off the I naught here because it's blocking. Okay, this purple graph has many values ranging from 0 to I naught square and 0 to I naught square. Okay, and I don't know if you know trigo. If you don't know, it's okay, but sine square is actually cos 2 theta. It's a double angle. Okay, if you have no idea what I'm talking about, that's also okay. Let's say I draw somewhere at half. Okay, so the halfway point between I naught square and this, and I'm going to eyeball it, okay, with my very accurate eyes. All right, so this line is half. Just slice it into half. Okay, so this will be I naught square divided by 2. And when okay, this one not very nice, BRB. Let me draw a nicer one. I naught square over 2. Okay, we're back. I've drawn the line of roughly where I think half is. And if you are going to stare at this, I'm just going to do it. So normally in a face-to-face class, I can cut this out and get you to do some arts and craft with me. But you will notice that this area that I'm shading now nicely fits into this hole or this empty slot here. Okay, just like let's say this area here, oops, too big. This area here nicely fits into this empty slot here, halfway, at the halfway point, somewhere here. So it nicely fits into here. Okay, so if this is the case, I can say that for one complete cycle, the average of I square is actually I naught square over 2. So if I bring this all together, then this box here, this one, okay, I'm running out of colors, but this whole thing becomes the this whole thing here for one cycle. This one becomes the average of I naught, oh sorry, average of I square for one cycle. But we know this motion is periodic one, motion, the alternating current is periodic. Meaning to say, right, when I put this area down and I repeat, the same story will perpetuate on and on and on. So this I naught square over 2 is actually the mean square current. Okay, it is the mean square current. If you're like, why is it over 2? Why not over 3? Why not over 2.5? Okay, you come down first. There will be a further physics video using expected values to explain this. And if you really cannot, then you just print out the graph, you draw the midpoint, you cut out this area and you paste it in. Because those are the activities that I used to do. Okay, so you could cut out this, it will fit nicely. So this entire area becomes the average of I square. So this means that the mean square current now is our beautiful I naught square over 2. Wonderful. Beautiful. All right. So if it's I naught square over 2, then we can now just zoom out again and think about what our definition is, or where did we started. We started by saying that, oh, we want to replace this AC with a DC. But because we want to label a number there so that the electrician, the people are doing all these power supply things, they understand that, oh, when I connect this to alternating current, this is the power output that I'll get. I don't have to think about the peak lah, I don't have to think about the frequency lah, I just need to find the power output. So if I want them to have the same power output, all right, what I need to do is I need to find a way to represent this current. Problem number one with the current is that the average is 0 because of the negative cycle. So what we did was we square the whole thing. When we square the whole thing, we can actually have a value of the average of that square. So the average of that square is known as mean square current. That will be the first step. We have this mean square current. So I'm just going to call this step 1, statistical treatment. All right, step 2. We are now ready to plug this into our definition. Okay, so what was our definition? We say that the power of alternating current, average, or mean power, is equal to the power of the direct current. But also at the same time, we know that P is equal to I square R. So we're going to just do some substitution, but this one is average of I square times R. And this will be the normal DC current square times R. But we look back at our circuit again. Our DC current is the IRMS. Okay, this IRMS, this one is our DC current. So we're gonna put the RMS here. Plum, plum, plum. All right, and of course your I and I can cancel. I'm sorry, your R and R can cancel. What am I talking about? Because there's a common resistor. Okay, and what we have left now in our equation is the mean square current is equal to the root mean square current. Lemao. Okay, so this I square can be written as I naught square. Don't be too hung up about the equations lah. Okay, so this is the average of I square. So whenever you write this one, okay lah, I draw the slide here for you, especially if you struggle a bit with maths. This I naught square over 2 is the average of the AC square. Okay, so meaning if I want to find the average of this purple graph, I just need to, purple graph square, or I square purple graph, I just need to take the peak, divide by 2. Peak, divide by 2. Or since the peak is square, so it will be I naught square divided by 2. Okay, so the peak of the purple graph is I naught square because we square the orange graph. So hence, I naught square divided by 2. Alright, so this one will be equal to I RMS square. And you know lah, who wants to deal with this kind of equation? So I'm going to square root both sides. You will get I RMS is equal to I naught over root 2. So the takeaway here is we want to be able to describe our alternating current without using trigonometry. And the only way to not use trigonometry is to find a way to obtain a mean square value or average, if you must, of the current. We have to square it because of the negative sign. And just so happen because when we square it and the negative sign, so good. Power also got I squared. So we can just nicely slot it in and cancel off the R. And we'll arrive at this RMS current as I naught over root 2. Ladies and gentlemen, boys and girls, if you don't understand the derivation, it's okay. But this equation, hopefully you can accept and use it or memorize it, I guess, especially if you're not doing maths. If you want to see me derive this, it will be in the bonus video. All right. So again, where did the 2 come from? Because the average of I square is I naught square over 2. If you don't know or cannot accept or want proof, you go back and print out this graph, cut it into half, and then you paste cut and paste see whether it fits nicely or not. It fits one because trigo works, pure maths works. Okay. All right. So what else do we need to know? Since we have the RMS current, we know from the equation V is equal to IR. So I'm just going to draw a line and write here. All right. Okay, we know from the equation V is equal to IR. V RMS will be equal to I RMS times R. Okay, so to find the root mean square voltage, you will notice that this I RMS is I naught times R over root 2. But this I naught R, V naught is also equal to I naught R, what? Because V equal to IR. So if I want the peak voltage, I will take the peak current times resistance. So if I want the RMS voltage, I will take the RMS current times resistance. Okay, so as long as it's consistent, RMS to RMS, peak to peak, it is okay. Now here, RMS must be together with RMS. Peak must be together with peak. Okay, so from here, I will get the final form of the equation. V RMS will be equal to V naught over root 2. Compare the form left to right. They are fairly similar, if not, I would dare say identical. Okay, this is only for sinusoidal. Let me emphasize this. Only for sinusoidal alternating current. What is sinusoidal? Nah, this one no, the wave one, the sine graph one. Miss, what if it's not sinusoidal? Will they ask? Well, they haven't asked until they did recently. So go and check out the example video. Okay, what happens when your alternating current is not sinusoidal? Which is why in this video I emphasize on the fact that actually the reason why there's this equation is because the average of this sine square happens to be the peak divided by 2. That's why you get a root 2 here. If it's not peak divided by 2, let's say they draw some other shape, then you need to be able to brain or think about the average. Okay, So don't worry, they won't draw too complicated shape. Normally it's boxes or squares or rectangles. All right. So what did we learn in this part? We learned that this value, this one here, this, where is it? There we go. This 0.5 ampere is not the I equal to I naught. Nah. Your I is equal to I naught sine omega t. This one is probably the IRMS, to which we can calculate using I naught over root 2. Okay, so whenever you see this, you're like, I know liao. This 0.5 is RMS. It's IRMS, root mean square current. Okay, so that part is here. And the second thing that you learn is that in order to define that root mean square value, we have to use this definition. The RMS value of AC is the value of direct current or direct voltage that will produce the same thermal energy or heating effect as a common resistor. Okay, so they need to have the same power output. Same power output as the common resistor. So once the power output is the same, the idea here is we need to find the average. But we cannot average sine because the average of sine is 0. So we average sine square, which also happens to help us because power is I square R. And for sinusoidal waves or sinusoidal shape, the average of I square is I square over 2. All right, the average of this one is I square over 2. So from here, we can use the definition of power, okay, or the definition of the equation. So this is step 2 here. The mean square, the mean of the AC circuit will be equal to the root mean square in the DC circuit. So by substitution, we came up with this and this. All right. So since power in the AC circuit is so important, just like power in any circuit, which is why we started off in the first place, we can now think about how to calculate power. There are two types of power. There is the maximum power in an AC circuit. Okay, there's maximum power in the AC circuit. I'm just going to call this P max lah, okay? Maximum power. This one, you will take maximum voltage multiplied by maximum I. Or I guess you could take I naught square times R. You can also take V naught square. V naught? Yeah. Over R. All okay. Right? But what about average or mean? Mean or average power? So you will have to take VRMS times IRMS. Okay? I'm not going to write the other iteration lah. You know what to do. Okay? So if I take the VRMS times IRMS, I will get V naught over root 2 times I naught over root 2. What is root 2 times root 2, guys? Root 2 times root 2 is V naught I naught over 2. So from here, you can see that your mean power is also equal to the maximum power times half. This one is important law. Okay, mean power is the peak divided by 2, or half the maximum power. Okay, and mean power also happens to be equal to, you will take, again, if it's average, then you average. So for mean, we will take RMS times RMS, because you're taking average times average. So basically, our statistical technique, which is a lot like finding the variance and standard deviation, is we square the numbers and then we average. All right, which is what we're trying to achieve here. So take some time to brain this if you're interested about the maths, to show that it is indeed 1 over 2. That will be in the further physics video later. Okay, try some examples. All right, so we learn what is root mean square, how we can use it to represent our direct current or relate our direct current to alternating current. Okay, so we did some statistical treatment to find the relationship of root 2. Some of you may be thinking, why is it so difficult? Why can't we just stick to DC? Why can't life be simpler and we only have direct current? Why can't my plug points be direct current? Why can't we just use direct current? Well, there are several reasons later in the following subtopic, for example, in transformers, where we talk about how only alternating current can be step up and step down. Meaning if you want to change the voltage of a current, only alternating current can do it for you. That would be the first reason. And the second reason here would be, if let's say your alternating current can easily be generated by turning this little motor here. You want to change to DC. It's probably quite a complicated process, right? Which that would be the third subtopic in this chapter. Okay, one of the next subtopic as well. And also finally, once upon a time in the late 1800s, yes, late 1800s, at the turn of the century, before the Industrial Revolution, you have these two person. I think you have heard their names before, I guess in very different way. You have the Edison versus Tesla. So at that point in time, humankind can already generate current. So they were building power grids and they were deciding, should we DC or should we AC? The band AC/DC. Should we direct current or should we alternating current? So to know whether we should use direct current or alternating current, they actually had a fight lah. There's an entire history here, okay? But let me tell you a bit about what Edison and who Edison is. Edison is a businessman. He's an opportunist. He's also very much a politician. Meaning he's the kind of person that right now, if he's alive, he will be the videos that you see in front of your, the ads that you see in YouTube telling you how to earn money in 2 months or whatever, okay? Whereas Tesla is a slightly socially awkward scientist. The problem with scientist people is that they are not always very good communicators because all their brain power is used to do science. To think of squaring currents like this, to find all of this. So you have a very smart but very socially awkward person, and then you have a businessman. So Edison wants to push his DC agenda because it's his company. He can earn millions and billions for all his descendants and generation and all his kids. I'm not sure how many kids he has. Basically, he can get very rich. Fella is a capitalist, okay? Whereas Tesla is like, I just want science. I just want the best science, the most efficient science. So Tesla used to work for Edison. Edison is older than Tesla. But they had a falling out or an argument because their values are different. So that's the first thing that we learned. Values matter. If you work with someone and the person have different values than you, then halfway along the line you will GG. Okay? So Edison tried to discredit Tesla, but eventually Tesla's science, because it makes more sense, won over Edison. But you see, Tesla, AC is not his most groundbreaking thing. He has more ideas. He has ideas for wireless transmission. Means we got wireless now. Dude, he has wireless at the 1800s or the 1890 something and 19 something something. Okay? So he has ideas for that at 100 years before this, but they were not translated because he didn't write down or share his ideas properly, okay, such that investors begin to pool money from his research. All right, so I think there are a few takeaway points here. Number one, you work with people who has the same values as you. Might not have the same methods or strengths, but they should have the same values as you. Edison cares about making money. He cares about being, I guess, powerful, whereas Tesla only care about the science. And because of the lack of respect between both of these, they fall out. And Tesla, due to his failure, became a social recluse and a bankrupt when he died at old age. It's useful to think about you see these people, they're like very, when you study magnetic field and you see the unit Tesla, that's his name, right? Tesla. And the car, Tesla. All right. So he is a really brilliant scientist, but unfortunately, he has not met someone that could complement his weakness to actually say, hey, you know what, Tesla, you do the science, I'll do the marketing for you. I'll promote this for you. You don't know how to communicate the science? Tell me, I will help you teach it to the masses. You don't know? Masses don't understand? I not sine omega t? Never mind. We just give them a number, 0.5 ampere. Okay, so people don't get scared. And the thing about Tesla is that part of who Tesla is he doesn't really care if you get it or not. So you need he could have done better if he had someone in his life, or if he was working with someone who is able to show him the importance of communication. Like, for example, if I'm very in love with physics, but I don't know how to talk to you about physics at your level, then something is lost in translation. But we all have our strengths and weaknesses. And I think the juxtaposition or the contrast between Edison and Tesla, the mad scientist and the businessman, okay, allows you to see that in the field of sciences, intelligence matter more, but ethics also matter more. Edison did a lot of things against what is right when he was trying to push his DC direct current agenda. He did a few morally reprehensible or questionable things. You can go and Google and find them. All right. So that's just a sidebar or a bit of history behind all the currents and circuit that you have in your life. Okay. Hopefully that was interesting to you. Okay. Anyway, I'll see you in the next video or the example videos. If you find this helpful and if you learn something, please comment down below. We'd love to hear from you or talk to me about this. And I will see you in the next video. Share the video with friends to learn physics together. Bye-bye.